Good afternoon, everyone, and welcome to this session, which I'm very happy to moderate and to facilitate today. My name is Letizia Tedesco. I'm a senior scientist at the Finnish Environment Institute, and I'm also an adjunct professor at the University of Helsinki, both located in Helsinki in Finland. I'm a polar scientist, and I'm looking at how sea is changing are impacting marine ecosystem, which is also the focus of our session today. And I'm very happy to share the stage with 5 fantastic polar scientists, which will cover different aspects of sea science. So we have on site Professor Stephanie Hart. Then we have online Josephine Rapp from Harvey Ocean. Then we have on site Jacqueline Stefan from University of Groningen. And we have online Sean Halley from University of Edinburgh and Professor Marcello Vicky from University of Cape Town in South Africa. And before we move on to the core, so before we move on to the core of this session, I just would like to spend a couple of words on what's behind this session. So this session is organized by VAPSI. It's a working group, and VAPSI stands for Biochemical Exchange Processes at Sea Ice Interfaces. We are a very large international network, and we focus on sea ice biochemistry and sea ice ecosystems. We produce typical products for science, like publications, but we also encourage early career scientists. We assist them in their career support, and we also try to make the sea ice topic accessible to younger generation. We have just published recently a special feature on Frontiers for Young Minds on sea ice. And last but not least, we also target as our audience policymakers. We already have published one policy brief focusing on Antarctic sea ice, and we are at the moment preparing another one on Antarctic sea ice. And since 3 years, we are contributing to COP with an increasing number of events. And for this, I would like to get started. So this is what we will talk about today. We will start with Stephanie. She will give us an overview of sea ice physical changes. Then we will move on to Josie first, and then we will have Jacqueline. They will talk about the impact of sea ice changes on Arctic and Antarctic marine ecosystems. And then we will have Sean. She will present risk and consequences and likelihood or unlikelihood of geoengineering sea ice. And we will close this session with Marcello, who will give us his perspective and some recommendation from a global south point of view. After that, I will open the floor for questions and comments, and you are all invited to the discussion. So, without further ado, I would like to call Steffi to the floor. Steffi is a professor at the Alfred Wegener Institute, in short, AVI, and she also holds a professorship in biospheric sciences at the University of Hamburg. Her research focused particularly on Antarctic sea ice, and she has been studying Antarctic sea ice on site for more than 10 expeditions. You want me to take it away? That's fine.
Thank you, Letizia. Thank you for all being here also from my end. And I want to start diving into the polar regions, and in particular into the sea ice region, by looking again at our general global ocean circulations. And I think we can't get tired of highlighting here the importance of the polar regions when talking about our global circulations. So what we do see is like cold water masses produced both in the Arctic and in the Antarctic. On the one hand, obviously, by the fact that we have cold atmospheric conditions in the polar regions, which hold and cool the surface waters. However, in addition, we have then the topic that I'm talking now about. We have our lovely sea ice on top of that sitting. And while we form sea ice in the polar oceans, most of the salt of the polar oceans is not incorporated into the sea ice structure, which causes that all the salt is like going into the ocean, sinking down to deeper ocean layers, where it forms our really globally important Antarctic bottom water masses, as well as our deep ocean water masses, which are therefore like really one of the engines of our global circulation system, as you can see. So now looking at how the sea ice evolution actually looks like, both in the polar regions in the Arctic and in the Antarctic, you can see now here on the left-hand side how the sea ice extent minimum for the Arctic evolved over the last years. So you can see really obviously already from the beginning that the Arctic sea ice minimum has like really decreased drastically over the last decades. In particular in summertime, we also see this change in the winter observation period. However, in particular in summertime, it's really pronounced, as we can see that we lost more than 50% of our Arctic summer sea ice over the last decades. In contrast to that, we see on the right-hand side the Antarctic sea ice also now moving, sea ice minimum. On the one hand side, we do see the big contrast between the Arctic and the Antarctic in the geographical setting. So we have in the Arctic, the Arctic Ocean sitting on top of the North Pole, surrounded by land masses. However, in the Antarctic, we do have the Antarctic continent sitting on the South Pole, surrounded by the Southern Ocean, and with that also surrounded by the Antarctic sea ice cover. However, also in terms of trend and evolution of the Antarctic sea ice, we observed quite some difference between the Arctic and the Antarctic, which means in the Antarctic, until 2015-16 roughly, we observed a slight increase or kind of a stable sea ice cover for the summer months of the Southern Hemisphere. However, since then, we do see a drastic drop both in summer and in particular also in last year's in winter months. And to highlight these changes, I just brought here again now the Arctic and Antarctic sea ice extent anomalies, where we can see again what I just mentioned before, that for the Arctic, we do see this negative anomalies, meaning this really dramatic loss in Arctic sea ice since 2 decades. Whereas in the Southern Ocean, this change just kicked in a couple of years ago. However, what we can also see in both hemispheres that these changes are kind of globally, meaning throughout the Arctic and Antarctic sea ice region. However, let's now focus first a little bit more into the Arctic, because when we talk about the Arctic sea ice, it's not only that we lose sea ice in terms of sea ice extent, but we also observe a drastic change in the sea ice age distribution. What you can see here now is on the left-hand side, sea ice age from 1985, on the right-hand side from the last year, from 2023. The darker the colors are, the younger the sea ice gets. And what you can see on the left-hand side is that most of the sea ice in the beginning of the 1980s was still old ice, meaning ice that survived at least one summer sea ice melt period. However, when we now look in recent years, it's really obvious that we lost more or less all of our old Arctic sea ice, and only the younger, much more dynamic, much thinner ice is just left back in the Arctic, which has, of course, also dramatic consequences. And these consequences are then also seen when we look into the sea ice thickness evolution of the Arctic sea ice. Here on the left-hand side, you can see just an example plot how the sea ice thickness is distributed over the whole Arctic region, derived by satellite remote sensing. On the right-hand side, you can see a plot on the evolution of sea ice thickness, again starting in the late 1970s from our satellite remote sensing data. Maybe just I concentrate here for the moment only on the blue and on the red lines, because those are the sea ice thickness evolutions for summer and for winter months in the Arctic from satellite remote sensing. And independent of whether we look in the Arctic or whether we look in the summer or in the winter period, we do see a drastic loss in sea ice thickness, which means when we now put all these information together, we have a loss in sea ice extent, we have a loss in sea ice, in old sea ice, and we have a loss in sea ice thickness, which means in the end that we have overall a drastic loss in sea ice volume for the Arctic Ocean area. Well, this is when we look into the Northern Hemisphere. When we now look into the Southern Hemisphere, I would love to show you similar graphs. However, the Southern Ocean, we do have still huge uncertainties and huge gaps in terms of knowledge. What you can see here now is on the left-hand side, the sea ice thickness derived against the satellite remote sensing data for March. And on the right-hand side, it's the uncertainty. And even though the color bar is slightly different between the left and the right plot, what you can easily see is that we have uncertainties of almost 50% when we talk about Antarctic sea ice thickness. So how should we come up here now with like conclusions about volume development over the last decades, about sea ice thickness development over the last decades? That's hardly impossible. However, what we do know for the Southern Ocean is that we have a strong warming of the whole ocean column in the Southern Ocean, which is then, of course, also spreading throughout the rest of the world, and also the other way around, just like what is warming in the rest of the world is also moving to the Southern Ocean, which causes then that the whole column of the ocean is getting warmer. And this warmth of the ocean, in addition to the heating of the atmosphere, has, of course, also in the Southern Ocean as well as in the Arctic Ocean, drastic changes for the whole energy budget of the polar regions. And therefore, let me guide through this plot here, or through this schematic here, when we talk about polar feedback loops and the amplification based on our global warming. So what is happening is that usually sea ice has a really, really high reflectivity, meaning that most of the incoming solar radiation, up to 90%, are reflected back into the atmosphere. This is what we refer to the albedo of the sea ice. However, when we only take the ocean now into account, for the ocean, most of the incoming solar radiation is not reflected back because it's much darker, but it's only like these 90% that were reflected back from the sea ice are basically absorbed by our oceans. When we are now like facing a time where we have this strong reduction in sea ice extent both in the Arctic and in the Antarctic, this means in the end that even more of the heat that is coming towards the polar regions is like absorbed by the ocean and is therefore contributing to even more warmth of the surface ocean layers, but at the same point then of course also accelerating further sea ice loss. And this whole chain causes that this huge importance of the Arctic and Antarctic sea ice areas that are kind of cooling our globe also, given that they are supposed to reflect all this incoming solar radiation back to space. This is what we are currently losing. And as a consequence of that, this is what we have just seen in the beginning of the week when the new report of the state of the cryosphere was just released here within the Cryosphere Pavilion. We can see that these changes have already drastic consequences for the radiation budget, both for the Arctic and for the Antarctic in respect to the global warming. However, this change is really strong, both for the Arctic and for the Antarctic. I think this is what we all agree on. And when we now look into the future, this is, of course, now also what we are also hitting here at this COP conference, looking here in future projections, both for the Arctic and for the Antarctic sea ice extent and concentration, what you can see here, is that the models have huge uncertainties still. In particular on the Southern Ocean, again, as I said, so we are not even able to describe how the current situation in Antarctica looks like, given our limited data. However, overall, we can all agree that the sea ice is going to shrink even more, in particular when we are just like continuing in terms of warming as we are currently doing. Because every degree that we are like crossing further just above this 1.5 degrees Celsius aim that we had, will cause that we will in the end lose even more of our Arctic and Antarctic sea ice areas and will therefore contribute to even stronger warming of our globe.
Thank you, Steffi. We are now moving on to our next speaker, Dr. Josephine Rock. She's a marine microbiologist, and she has 10 years of experience researching microbial ecology of the Arctic Ocean, specializing on cryosphere and deep sea ecosystem and their response to environmental changes. After working at the Abbey and also University of Laval in Canada, she is now the scientific coordinator of the REV Ocean research and expedition vessel, which once operational will serve as a platform to develop solutions to the ocean challenges caused by climate change, plastic pollution, overfishing, and environmental impact of fishing. And today she will bring us in the fascinating world that is life in Antarctic sea ice. And Josephine, whenever you're ready, the floor is yours.
Thank you
And
very
I
much,
will change the slide for you.
Okay. I hope you can all hear me okay. Thank you very much for joining on site and also online. Like Letizia said, I would like to talk to you about the role of Arctic sea ice as an important habitat for microbial life, which easily goes unnoticed, but is essential for the biogeochemical balance of the Arctic ecosystem. Next, please. Invisible to the naked eye, a piece of sea ice like this one shown in this photograph is home to millions of microbes. Next one. If we were to take a microscopic cross-section in this little frame that I've highlighted there, next one, we would see a matrix of ice crystals permeated by channels and pockets of brine that can remain liquid year-round due to high salt content. Next one. Looking at a sample of sea ice brine under the microscope can just be as mesmerizing as looking at the night sky. This photograph here shows the brine community found in the center of a thick multi-year ice flow. And I have stained the organisms with a fluorescent stain so that you can clearly see them. In just 1 milliliter of sea ice brine, we can find millions and millions of microorganisms. Sea ice supports diverse and active communities of viruses, bacteria, archaea, algae, grazing organisms, and fungi. And to be able to live under the strongly fluctuating temperatures and salt concentrations in sea ice, these organisms require unique adaptations. And as a result, sea ice habitats make an important contribution to global biodiversity because they support species that cannot be found anywhere else. Many of those have not yet been formally described, and their ecological roles are still unknown. Primary production by sea ice algae fuels the food web and feeds higher trophic levels, such as crustaceans. And together, the activity of these microorganisms mediates the cycling of nutrients and carbon and regulates the exchange of gases and organic compounds. And lastly, I would also want to stress that the extreme environmental conditions in sea ice facilitate genetic exchanges between organisms, and therefore sea ice also has an important relevance for the evolution of marine life. And with emergent technologies, this is something that we are only starting to really explore. Next slide. Sea ice supports a variety of microbial habitats, as you can see in this schematic, both on, in, and under the ice. And I would like to point out that these, here in this picture, these communities are not drawn to scale. The composition of these communities varies, and also in their density and the activity of these communities, we see variations depending on the type of habitat we're looking at, but also throughout the seasonal cycle. And we find differences between different types of sea ice. So for example, the communities in young first-year ice looks very different from communities that we find in thick multi-year ice. And I want to note that it's still quite difficult to study sea ice communities, and that is for several reasons, be it their ephemeral nature, but also due to the challenges of adequately reproducing the harsh environmental conditions that we find in sea ice in the lab, and finding non-disruptive sampling techniques. So the list is very long. And as a consequence, much of the diversity and the unique ecologies of sea ice microbes still remain to be discovered. Next slide. However, we do know that the activity of microbes in sea ice is just one piece of the puzzle of a highly complex system. I will not go into all the details that this graph here depicts, but we have to think about the fact that sea ice is the interface between ocean and atmosphere. And so the physics of sea ice and the biogeochemical processes in sea ice directly impact the physical and biogeochemical processes in the air, in the water column, and even the benthos, for example, through the flux of gases and also the export of organic matter. And therefore, the biogeochemistry of sea ice directly and indirectly impacts the climate system, pelagic and benthic food webs, and also those that depend on it for sustenance and business, like the indigenous communities of the North. Next slide, please. With continued dramatic warming, many of these unique microbial ecosystems that Arctic sea ice supports, as well as the coupling of these processes, are under threat. And this graph here shows the yearly temperatures in the Arctic in red compared to the global average in black. And as you can see, the Arctic is warming more quickly than the rest of the planet, a phenomenon known as Arctic amplification, which Professor Arndt just introduced. Next slide, please. The most obvious effect, as well as a cause of this amplification, is the rapid decline of the Arctic sea ice cover. And in this map that you have also just seen, I want to highlight that the youngest, thinnest ice is shown in dark blue, and the oldest, thickest ice is shown in yellow. And what scientists have been observing over the last decades is that sea ice is not only declining in extent, but the remaining Arctic sea ice is also getting thinner and younger. And while more than a third of the pack ice was at least 4 years old in the mid-80s, today most of the Arctic sea ice doesn't survive the summer melt period. And scientists agree that the Arctic will be ice-free during at least part of the summer, but the question is how soon? And a recent study concludes that ice-free conditions in September are likely to occur by 2050, if not earlier. What you can also see in this map is that there's a very thin residual band of old multi-year ice that spans along the northern coastline of Canada and Greenland. Next slide. And the main reason for the formation of this band is a combination of ocean currents, in particular the transpolar drift and the Beaufort Gyre that deliver the sea ice over thousands of kilometers from across the Arctic basin. And this ice then piles up against the coast to produce an area of oldest and thickest ice in the Arctic Ocean. And this ice is projected to remain the longest, even after the rest of the Arctic has become ice-free during summers, and it has therefore been named the last ice area. It is considered to be the ultimate refuge for ice-dependent marine life, and here I'm not only referring to the microbial life, but also to large animals. About a quarter of the world's population of polar bears live there or near there, and most of the world's narwhal whales spend at least part of the year there. Next slide, please. In 2019, Canada put part of the last ice area under interim protection by establishing the Tuvalu-Ituk Marine Protected Area. Tuvalu-Ituk means the place where the ice never melts in Inuktitut. And the temporary status of protection has just been extended by another 5 years, while the government of Canada works together with Inuit and Northern partners to define the long-term protection priorities in the area. This area is not only unique due to the presence of these disappearing multi-year ice ecosystems, but it has also long been used by Inuit for travel and harvesting, and so it's also of cultural and historical significance for the people in the north. And with this, I would like to come to my final slide and end this presentation with a couple of take-home messages. And I think the most important that sea ice is a living system with very complex linkages to the physical and biogeochemical processes in atmosphere and ocean. And so that means that whatever changes the biogeochemistry of sea ice is going through, there will be implications for the larger Arctic system. And these dramatic losses that we have been seeing now for decades are a sentinel of human-made climate change. And the only way to slow down the loss of sea ice are drastic reduction of greenhouse gas emissions. And on top of that, we really urgently need implementation of long-term protection strategies for the remaining sea ice ecosystems that we still have. And we should not forget that we can only adequately protect, or we cannot adequately protect what we don't understand. And so there really still is need for further studies on long-term monitoring for us to fully understand the seasonality, the biogeography, and the complex ecologies of life in the Arctic Ocean. Thank you very much.
Thank you so much, Josephine. And we move on to our next speakers, who is Dr. Jacqueline Stefan. She is based at University of Groningen in the Netherlands. She's a senior scientist and a lecturer, a marine biology expert on the role of microalgae in the regulation of climate gases, especially within the CS system. And she has also been in multiple expeditions in the Arctic and in the Southern Ocean. And last but not least, I forgot to say that she's the BAPSI chair, and she's together with me, but she's also one of the two founders of BAPSI. And sorry if I didn't say that before. We are very quickly moving on the other side of the world, and she will talk about the impact of ocean changes on Antarctic ecosystems.
Thank you, Leti. I'll do my best to speak up and make this understandable for you. So we are moving to the Antarctic, and obviously many of the processes in the Antarctic are similar to what is happening in the Arctic, but on a different scale and with different organisms. So very often a graph tells you more than what words tell you. And here you see a different view of the world. And it shows you how immense actually the cryosphere is relative to the terrestrial system. And of course, sea ice in this picture is about half of what you see here. But the Southern Ocean, covering 18 million square kilometers in winter, compares to the tropical forests and also to coastal oceans. I want to ask you to keep that in mind, because I'll come back to that in my last slide. So sea ice is important for the ecosystem of the Southern Ocean, and in several ways. So the Southern Ocean sea ice is very rich. It contains 1,000 times more algal biomass than in the underlying water. And in the top pictures of this graph, you see how dense it looks. And that also means that it is a very luxury dinner for especially krill that lives on it. And of course, after krill, you get it impacts on the food sources of penguins, of whales, of seals, etc. So these beautiful unicellular algae are the primary source of the total food web. Not only is sea ice important for the ecosystem, it's also important for the chemical cycling of climate-relevant elements, such as carbon and sulfur. So sea ice is not only important because it has a cap, it forms a cap on the ocean, as Steffi just mentioned. Of course, that is very important for the reflectivity of sun rays, but it's also very important because it impacts on the cycling of climate-relevant compounds such as CO2 and sulfur cycle. So algae, they take up CO2, and they can form actually an important sink of CO2 that brings CO2 towards the sediments, and that it is the only way of really getting rid of the CO2 from the atmosphere. It's also, Antarctic sea ice is also a very big source of a compound called dimethyl sulfide. It's a very strong source for condensation nuclei. Thereby, it creates clouds, and clouds cover the Southern Ocean, and thereby regulating the regional area. So, what is happening with when climate is changing? So, in short, it shifts from a polar system to a subpolar system. The Western Arctic Peninsula is one of the most studied areas around Antarctica. It has a long-term program from the Americans that started in 1992. And they've seen this to shift from a polar to a subpolar system. What does that mean? That means a polar system, when you have a lot of ice cover, means that the underlying water is very relaxed, and there's not much wind mixing in there, and the result is that this dense algal bloom that forms the food of krill goes directly towards the higher trophic levels. That means there is it's a short food chain with a high quality. Now, if we see that things are going to change, that means that there is less sea ice. That means that wind mixing can have a much bigger impact on the whole system underneath the ice. That means that there will be a change of the larger algae towards smaller flagellates. That has an impact on the larger trophic levels, but much longer food chain, a much lower food quality, and a much lower export of CO2 towards the bottom of the sea ice, towards the bottom of the sediments. So that has a big impact in the longer term role of sea ice in climate gases. But this not only has an impact on the small food web, it also has cascading effects on the larger animals. So krill is dependent for a large part of its stages, habitat on the winter sea ice, where it has the small krill feeding at the underside of the ice, and it really needs high density algal blooms. However, if that sea ice changes, then it will shift towards south. South will take over. That's the lower ones. You see, it's kind of a bag of water that filters the water instead of grabbing the food from the ice. You can see that a bag of water has a lower food quality than nice and crispy shrimps, right? So this will have cascading impact on the higher trophic levels. As an example, here the beautiful emperor penguins that not only rely on the higher trophic levels, the fish and the krill, but they also have their chicks breeding sitting on the ice. They breed on the sea ice for a large extent, and we've seen catastrophic breeding failure in only 2 years ago, when the sea ice broke off and the chicks hadn't fledged yet. They were unable to swim, and they all drowned. And that is what is actually predicted to happen. By the end of the century, we will have only maybe 3% of the emperor penguins left if we lose the sea ice, which would be a devastating thing. So I mentioned sea ice is not only relevant for the ecosystem, it's also relevant for climate regulation. I mentioned that when sea ice disappears, you have much more mixing of wind mixing, and that means that the exchange of gases between sea ice and the ocean and the atmosphere will change dramatically. But basically, if you look at this rather complex figure, you see a lot of white question marks, which means that we actually don't know how that will impact on climate itself. So I mentioned it's very important for regulation of CO2, but also for cloud formation. But whether it will go up or it will go down is actually largely unknown. So, take-home message from my talk: a change in sea ice will result in large shifts in algal blooms. It will change in different characteristics of algal blooms. This will have cascading effects on a unique ecosystem. And basically, maybe people haven't really realized, but the habitat loss when we lose sea ice is comparable to the destruction of coral reefs and rainforests. We are all very concerned about those, but we should be very concerned about losing this unique habitat that is associated to sea ice. What the feedback impact on climate is largely unknown. So we really need to unfortunately, as a scientist, I have to say it, but we just need to do more research on that. But one thing we know for sure is that we have to keep the temperature below 1.1 degrees increase, because things are already changing far too much. Thank you for your attention.
Thank you, Jacqueline. And I would like to invite now Shan. She's our next reader. Shan, our next speaker. Shan, she's a reader in marine science and a research focus on the processes supporting ecosystem in the Southern Ocean and the Arctic, and how these processes influence and are influenced by climate change. She has been taking part in the last 3 COPs and is currently co-chair of the Southern Ocean Observatory System, in short, SOOS. Today, she will talk about the risk and the consequences and the likelihood, or rather unlikelihood, of success of geoengineering sea ice. And when you are ready, Shan, please go ahead, and I will change your slides.
Thank you, Letizia, and hello, everybody. It's lovely to be able to join you from here in Edinburgh. I hope you're all having a good conference. So, yeah, it's my remit this morning to talk about geoengineering of sea ice, and in particular, perhaps to provide a scientifically informed reality check and to really raise awareness of the risks of these approaches, the very likely unintended consequences, and the unlikelihood of success. So I'm aware that there's probably a mixed audience. The disadvantage of being an online speaker is that you can't see who's in the audience. So I hope it's a mixed audience, and I hope that we can have a fruitful and respectful discussion on this issue. Next slide, please. So there has been an increasing focus on geoengineering or climate interventions in recent years, which are proposed as a potential option for addressing the climate crisis. And this is on the basis that decarbonisation is occurring too slowly and atmospheric carbon dioxide concentrations are continuing to rise, despite the climate pledges that have been made at COP after COP after COP. And there is a very large and ever increasing investment in these geoengineering approaches. Now, it's important to note that this investment is primarily by private investors and philanthropic entities, and many of these have vested interests in the fossil fuel industry or carbon-intensive industries and lifestyles in general. So there are very strong interests in continuing business as usual with high carbon emissions to support business interests and financial gain. And geoengineering approaches have been proposed to create something of an illusion of a climate solution and to distract from the real priority of reducing greenhouse gas emissions. Now, this debate and this discourse has had a surprising lack of involvement of the polar scientific community. In some cases, scientists have been involved, but their opinions are largely unrepresentative of the majority of the polar scientific community. So there has been an inadequate inclusion of our collective understanding of polar dynamics and responses to these potential interventions. So next click, please. So there has recently been a concerted effort by many more sea ice and other polar scientists to provide some scientific objectivity and some unbiased scientific insight into the debate. So this paper is publicly, freely available online. It was published just a couple of weeks ago, and it was a group of over 40 polar scientists who came together to provide some scientific evidence and integrity into the debate around geoengineering. So what we did is we chose the 5 leading approaches, and by leading, I mean those that have gained the most attention in the media and public discourse, and we subjected these 5 proposed approaches for the polar regions to an objective and comprehensive test regarding its use in the coming decades. Now, of these 5 approaches, 2 of them are focused on sea ice. So it's those approaches that I'm going to talk about in this sea ice focused session. Next slide, please. Thank you. So the first approach that has been proposed for sea ice management is modifying the albedo. So cast your mind back to what Professor Arndt was saying about the reflectivity of sea ice and the fact that as sea ice is lost and changed in its characteristics, it has a lower and lower albedo, and therefore we see a reduction in the cooling effect of sea ice and therefore enhanced solar heating. So this first geoengineering approach is proposed as a means of scattering glass microspheres on first-year Arctic sea ice in order that its albedo will be increased, its reflectivity will be increased, and this will promote its survival through the warmer summer months to the following winter, which will re-establish multi-year sea ice. So that's the proposal. Next slide, please. And our scientific test that we subjected all of these geoengineering approaches to showed that there were significant risks and unintended consequences. So the first is the very real likelihood that these beads will be toxic for organisms. And this is all sorts of organisms from very small to very large, vertebrates and invertebrates. And the most likely group of organisms to be affected are zooplankton. And that's because when they feed on the phytoplankton that Dr. Stefels talked about. And the glass beads that will be deployed as an intervention are similar in size and therefore will disrupt the feeding apparatus of these zooplankton. And they underpin the entire food web, so this could have dramatic cascading consequences throughout the entire ecosystem. And then there's also the problem that glass beads are likely to dissolve in Arctic surface waters. So this will have a profound effect on ocean chemistry and ecosystem functions, which are very fragile in a very fine equilibrium. And therefore, these natural systems will be fundamentally perturbed. And of course, if the beads are dissolving, they're becoming much less effective at what they're supposed to be doing. So this dissolution will also reduce the efficacy of the proposed method. And it's worth noting that any means used to decrease the solubility of the beads will enhance these concerns around ecotoxicology. Okay, moving on to the feasibility or the likelihood of success. It's been estimated that enormous quantities of these glass beads will be required to make any meaningful difference to the trends that we're seeing in Arctic sea ice. So the central estimate that has been made is that 360 megatons of these glass beads will be required per year. Now that, for context, is equivalent to the annual global production of plastic. So not only will there be significant logistical challenges, and in fact, it's unlikely to be possible to operate at the scale required to make a difference, but we'll also be deliberately polluting this fragile marine environment. And then, of course, there'll be vast amounts of carbon dioxide emissions as a result of the production of these glass beads in the first place. And there is also a study that shows that these glass beads can have a net warming effect on Arctic sea ice and therefore accelerate ice loss rather than preserving it. And finally, there are major governance challenges with this technique, primarily because Arctic sea ice moves, and it moves rapidly over large distances. So with the complicated geopolitical space in the Arctic, there is very likely to be tension and perhaps conflict between nations that agree to this technique and those that do not. And it's particularly important to note that there will be severe implications for the Arctic indigenous communities who depend on these natural systems for their food, their livelihood, and their entire culture. So really need to be considered first and foremost in any considerations of interfering with that delicate natural balance. Next slide, please. So the second approach to managing Arctic sea ice that has been proposed is to artificially thicken the sea ice. Now, this is based on the premise and the truth that thinner ice is more vulnerable to faster melting during the summer, and this exacerbates the sea ice losses that are being observed. So the proposed intervention is to pump seawater onto the ice surface or into the overlying atmosphere, which will then freeze and fall as snow. So either of these approaches will thicken the sea ice during the winter, increasing its longevity through the summer and therefore making it survive for longer. And there is one study that has shown that this could potentially be powered by wind turbines. Next slide, please. I'm getting a strange echo on my end. I hope I'm still audible in the room. So in terms of the feasibility and likelihood of success, this is the major downfall of this proposed technique. Sea ice thickening, according to our objective scientific assessment, is simply not feasible for use at a scale and a rate that would be meaningful for sea ice protection. So, allow me to explain. The long-term average Arctic sea ice extent varies between the summer and the winter from 5 to 16 million kilometers squared. And the winter cover is consistently above 10 million kilometers squared. So if we make the assumption that one seawater pumping device can cover an area of 1 kilometer squared, and this is probably an overly optimistic estimate, but if we believe it, then that would mean that over 10 million devices would be needed to cover today's winter sea ice cover. Now, there is a study that has suggested that only 10% of today's winter sea ice cover would need to be covered by these devices in order to make a meaningful difference for sea ice protection. So if we believe that, then we still need over 1 million devices. And if we make an estimate that 1,000 devices can be deployed per year, and this is a colossal undertaking and arguably an unrealistic estimate. But if we believe it, if we believe that we can deploy 1,000 devices per year, it would still take over 1,000 years to cover 10% of the present Arctic sea ice cover. So there is simply not enough time for this proposed intervention to make a meaningful difference to Arctic sea ice cover. And if we do go ahead and action this water pumping technique, this would cause severe disruption to the natural balance and the processes in surface waters, sea ice, and the lower atmosphere, and the exchanges between them that Dr. Stefels and Dr. Rao both talked about in their talks. So even if it were to work and to be deployed in a meaningful way, which I've shown that it can't be, but even if it was, it would cause significant damage to these fragile ecosystems that we just can't afford to make. And similarly, with the glass beads idea, there are significant governance issues with proposed sea ice thickening approaches, and these will be related to governance structures both nationally, locally, and internationally. And this is particularly the case because this technique would require unprecedented human presence in the Arctic for construction and year-round maintenance over a vast area. And again, in common with the glass beads idea, there would be major transboundary issues because sea ice infrastructure would be moved with the sea ice across boundaries. So this, again, would cause significant tension between nations that agree to this approach and those that do not. And the governance issues are likely to be particularly severe around the maintenance and the eventual removal of these technologies, and also the what will likely happen quite a lot, which is that the pumps would sink when the sea ice melts or breaks up, and therefore are just dropped into the Arctic Ocean, which we know is a very fragile ecosystem. And all of these governance issues are particularly intense because the Arctic Ocean, as most of us will know, is becoming an increasingly congested and contested space. And as always, when talking about the Arctic and human activity within the Arctic, it's of absolute paramount importance to prioritize and to raise the voices of Arctic indigenous communities. And this is the case for any proposed climate intervention in their Arctic homeland. Next slide, please. Thank you. So according to our assessment, we find that no current polar geoengineering idea passes an objective and comprehensive test regarding its use in the coming decades. For the proposed approaches for sea ice management discussed here, they are simply very unlikely to make a meaningful difference to the climate and the sea ice trends that we're seeing over the timescales required. Further, many of the proposed ideas are dangerous for the environment and for people, with severe risks and negative consequences, as well as major governance issues. So we conclude in our study, and as a majority polar scientific community, that polar geoengineering approaches are a dangerous distraction from the real priority, which is to reduce our greenhouse gas emissions dramatically through immediate, rapid, and deep decarbonisation, leading to net zero emissions by 2050. Thank you.
Thank you so much, Sean. So we are moving to our last speaker, Marcello. Marcello Vicky is a full professor at the Department of Oceanography of the University of Cape Town in South Africa, and is the director of the Marine and Antarctic Research Center for Innovation and Sustainability, in short, MARIS. His research interests are linked to interdisciplinary Earth system processes, coupled physical biogeochemical modeling of the global ocean, observation and simulation of sea ice dynamics and biochemistry, Antarctic policies and infrastructure, climate change impacts on marine and sea ice ecosystem. And today, Marcello will give us some perspective and some recommendation from a global South point of view. And when you're ready, Marcello, the floor is yours, and I'll change the slides for you.
Thank you very much, Letizia, and I'm joining in from Cape Town. It's a pleasure to be hosted in this session, and good day to everyone, also everyone online. So I would like to continue along the lines of human-environment interactions that have been so excellently introduced by Dr. Sean. And I would like to highlight three main points that I actually have only 3 slides, and each one is dealing with one of these keywords that I consider rather important. So unfamiliarity, diversity, and urgency. So the risk of geoengineering are not in taking actions. We do need to take very quick actions and urgent actions, but rather in performing those actions on unknown complex systems. And sea ice is very unfamiliar to many people in the world. So there's a simple explanation which you see clearly in this slide and in the pictures in front of you that are now depicting what you have seen several times in the previous slides, the Northern Hemisphere sea ice in the Arctic and the Southern Hemisphere sea ice in Antarctica, but now they're drawn to scale entirely. So by looking, for instance, at that link that you see down there, and you will be able to maybe explore later, you can play with it and turn it around and see the real shape and how big, and also to animate all of them. This is a simulated sea ice thickness simulation data that you can't get from space, as explained earlier on. But what I would like you to focus on mostly is taking the 50 degrees parallel in the north and in the south, and see how many land, countries, people are actually in the north that they feel, perceive, and have some familiarity or perception and actions and needs related to the Arctic conditions. So we have polar countries that have direct vested interest in all of that. Now, look from the south, and you will see that the same parallel doesn't have any land besides just the tip of South America. It touches continents, extremely important continents, but Africa is barely visible in there, and then you got Oceania on the other hand. So I'm a representative of a Global South polar scientist. Of course, I can't speak on behalf of the entire Global South, but I really would like to give you some perspectives from this viewpoint. South Africa in particular is one of the original 12 signatory countries of the Antarctic Treaty, and it's the only African country that has direct and formal activities of science and relationship in the biggest common on Earth, that is the Antarctic system. So what is familiar to the global North, for the reason that I just explained, it's a lot less familiar to the global South. Raising a sense of awareness and political participation is therefore more difficult. And most of that, it's even more difficult when you have inequality involved. And this is so typical in the African continent. I mean, it's part of the functioning of the African continent at the moment, that change very quickly. It creates further separation when it comes to science and political priorities and investment. And you can understand when a government has to decide where to distribute research money and knowledge to increase and improve our knowledge from the South, that becomes more difficult. The next slide, please. Only pictures now when talking about our diversity. The two poles are different geographically. Professor Arndt has explained it very clearly. The science of sea ice and polar ocean has been evolving by extrapolating knowledge from what we could measure in a way more easily in the Arctic, because we can actually validate some of our remote sensing satellite measurements that are essential climate variables. But if you can't validate and you can't translate them into the real data and real value, then it becomes more limited, their use. They become derived data. So there's much diversity that I'm trying to show you here in these pictures, much diversity in sea ice type and conditions. And we have enormous data gaps in our understanding of sea ice, and especially in the Southern Ocean sea ice that is by nature thin and younger. It is mostly seasonal. So every year it disappears and comes back. So there's a complete difference from the functioning in Antarctic. And we have directly observed a tiny portion, both in terms of space and time, of this enormous and quickly changing system. So the pressing research priorities are to understand how susceptible this diverse environment is to the changes. And these changes are ongoing and dramatically becoming quicker. So the ice was studied, the ice that we studied in the 80s, actually the scientists that have been, and the knowledge that they created is different from the softer young ice that we are experiencing today. So we have to review all of that. We are navigating uncharted icy waters in this particular case. We are measuring a system that continuously evolves and modifies. So concerted research efforts that involve multiple countries, and particularly countries from the South as well, are essential, must be organized. And we need to consider, again, the diversity of infrastructure availability to the various countries. South Africa, as I said, is the only African country with formal polar science activity. And the person you see in the middle is a young scientist from the Democratic Republic of Congo. So landlocked nation, Central Africa. You can clearly understand and realize that the unfamiliarity of all of this. First time this person saw the ice on an expedition and experienced those conditions. Experienced with frostbites, particularly, because it's unfamiliar. We all know what's going on when it's too cold. But if you have been living in a country that has no relationship at all with that one, then it's entirely unfamiliar. He now knows directly on his skin, to be very precise, how diverse and unfamiliar all of this is. But we can't take everyone to an Antarctic expedition. That's entirely unfeasible. And it is so important that we raise all this awareness. So there's a large young human potential in the global south that would contribute to the knowledge of the polar system. And we are disconnected maybe in terms of understanding, but we are all connected through the climate. And we cannot wait for all the studies to be completed. Sea ice is vanishing too quickly. And we need to act even if we don't have all the information. And I'll conclude with my next slide, which is now showing again. Next slide, please. Which is showing again on a slightly different way the anomalies that has been shown earlier by Professor Arndt. But now I'm looking at the monthly variability over 1979 to now, which is the period of observations we have. It has already been highlighted before and stressed that since 2015 and 2016, many changes have happened in the Southern Ocean. And you can see the difference here with these two plots. We had an unprecedented retreat of ice in November. It's natural that is melting, but it happened so quickly. Natural cycle greatly accelerated. Since then, multiple winter and summer minima have been recorded. In 2022, in one of our expeditions, we experienced in just a few days the melting in full winter of several hundred kilometers of marginal ice zone that was never observed before. We don't know whether it's happening every time because we don't have expeditions going on there every time, and from space we can't detect those information. So the Arctic is showing undoubtful signs of declines in multiple aspects. It's not a matter of the if, it's a matter of the when, as you heard. In Antarctica, Antarctica, anthropogenic warming is likely to surpass natural variability that you have seen. This line that is continuously playing and dancing around that horizontal line, and then now we are becoming negative. It may come back because it's a natural system, but its complexity is the most basic, the most important part. So diversity, again, it's completely different to deal with a big ocean like the Southern Ocean, and then a very tiny continent in between when compared to the Arctic. Now, anthropogenic warming is winning over, and our simplified, and we didn't have much confidence in our climate models, have we heard, but they actually have been predicting this change. We still have limited confidence in the sea ice component in our climate models, but that doesn't mean that we can't take action because of that. A future with vanishing ice is very likely. Sea ice will be much better off with this, with a 1.5 degrees cap and a concrete action related to just transition towards decarbonized economy. This is an essential and urgent need for all of us. Thank you.
Thank you so much, Marcella. So we arrive at the end of this journey, the Sea Ice World. We would like to all leave you with these take-home messages. We are really running out of time, but I want to have some time for questions. So I would like to invite Jacqueline here and Stephanie, and I offer the floor for questions or comments. And please speak up, or I will repeat the question for you. And if there are no questions yet, maybe I will start because we are a COP. I would like to ask actually to each and one of you if there is one single thing that you would like to take out from this pavilion, what would be? That you would like to move it from here and go to the other side where there are actually the negotiations. And maybe we can start with our first speaker, Stephanie.
Yes, I think my main message, and I think this is the message that we started really to convene here for all the sessions that we talked here about sea ice, is really that for the sea ice cover, it's not an option to go beyond 1.5 degree, because beyond 1.5 degree, we will lose even more of our sea ice, and with that, the whole topic of the amplification of the heat storage and so on is just drastically increasing.
Thank you. Would you like to say something, Josephine?
Sure. Maybe one important message from my talk to take away is that the ecosystems we find in sea ice truly are unique. You cannot find them anywhere else on the planet. They have very important roles for the functioning of the polar systems, and we cannot replace them with any other cold environments. They can only be found in sea ice.
Thank you. Jacqueline?
Yeah, I can only reiterate maybe what Josephine said and add to that again, that when we lose sea ice, we lose a biodiversity that is comparable to the rainforest and the coral reefs. We are all concerned about that, but we should be concerned about what we lose when we lose the sea ice.
Thank you. And Sean?
Thank you, Letizia. Yeah, so mine following on from my hopefully strong message about polar geoengineering approaches is that the only real solution to sticking to the 1.5 degree target, or as close as possible, is to rapidly decarbonize as a global community. And that in comparison to sea ice geoengineering approaches, this is the only responsible, ethical, and equitable way to meet our shared challenge.
Thank you, Sean. Marcello?
I can't see the room, so I don't know who's attending, and I have a wish and a hope that there are delegates from African countries that have been listening to all of this, and when they go to negotiation, they would keep the message, the last point, that polar countries, they belong to them very much.
There is right no one in this moment, but there has been several of them attended this pavilion. This is what I can say. Any other comment or question? Yes, please.
I have a question. I think this is probably for Sean. I'm Geraldo from the CSC IT Center for Science in Finland. I'm very much interested in geoengineering, atmospheric engineering. It is really fascinating to hear about the geoengineering of the ice. But there will probably be also some initiatives to be changing the atmosphere. Have you looked into for example, if some country decided to put some ash in the stratosphere to reduce the temperature in the world, that's something that you can't really control globally. Have you looked into that kind of, I would say, threats and how they would affect the biosphere as well?
Did you hear the question, Sean?
I think so, yes, and thank you for the question. So I said that we assessed 5 approaches, and I only talked about the 2 that were focused on sea ice. So the other 3 were injecting sulfate aerosols into the atmosphere, modifying the movement of ice sheets by draining fluids from the bottom of them, and building seabed curtains, or walls or curtains in front of glaciers in order to prevent warm water flowing underneath them and accelerating their melting. And our scientific and objective test showed that none of these approaches are viable options. So really, we must prioritize decarbonisation as individuals, as communities, and as an entire society.
Thank you. This is exactly the answer that I wanted to hear, and I would love to read more about this if there's a paper about it.
Yes, there is. Perhaps my colleagues in the room could direct you towards the paper that we have recently shared and other literature on the matter. So thank you.
Thank you.
Thank you, Sean. Any other comment or question?
That is very important, but who's funding all of these studies? And how do we take action?
Who is funding all these studies? Okay.
Ourselves.
Marcello, do you want to say something about research priorities and funding, perhaps, also from your perspective?
How we can mobilize funding for this important funding?
You're absolutely right. We cannot hear you, Marcello.
Can you hear me?
Yeah.
Can you hear me? Yes. Okay. Thank you.
Perfect.
Yes, funding is a priority, especially when we're dealing with countries that have other priorities. At the moment, most of the science going on in the remote southern hemisphere is funded by the countries that got Antarctic treaty interests, that they are participating and signatories and are associated. So that means that there is some bias towards the countries that got more funding available for all of that. But I would say that 80% of the funding are governmental funding. There are a few possibility for donors. Unfortunately, most of this is going towards geoengineering approaches instead of going towards learning more about our system. But that is, I would say, it's complementary and very limited. So it's more from the governmental viewpoint that this funding is coming.
So there is glaciers, year of glaciers next year, 2025. Tajikistan is a country. Tajikistan. Yeah. So my question is, how do we work together to really raise awareness, so get more funding, get more attention from
Did you hear the question?
players?
Did you hear the question? Yeah.
The monitor. So the question is, the UN declare Tajikistan as a country for next year, glaciers year, glaciers year. So there will be a glaciers event in Tajikistan. It's another Central Asia region, very low income. So glaciers melting there also. So how does that relate?
So the question is, how do we raise awareness in order to get more funding?
Yeah.
And you were talking particular about this next year of glaciers.
It's the UN
UN
year.
glacial year. Yeah. Does anyone want to take this? Please go ahead, Sean.
Thank you. Yeah, thanks for the question. I think it's a really interesting one and a very important one. And ultimately, I think the answer is to appeal to people. We're often told as scientists that there are some audiences where we speak from the brain and some where we speak from the heart. And I think in terms of instilling action, really speaking from the heart is very important. So with particular respect to your question, I think the most tangible service that the glaciers provide is in water resources, and the very real threat that as those glaciers disappear, those water resources are compromised. And this is something that affects everybody, no matter how young or old you are, what you do with your life, where you come from. It is an issue that we all share and we all need to address together. So that would be my suggestion, that this issue could be captured as a provider of water, which is ultimately a provider of life for all. So best of luck.
Thank you, Sean. Does anyone want to add anything also, my speakers? Otherwise, if not, I would like to thank all of you here and online. I would like to thank the Cryosphere Pavilion for hosting us, everyone for coming. We will stay here for a while if you have more questions. But if my online speakers can stay for a second, we will take a picture with you. Thank you.